For thousands of years, humans looked up and saw a perfect, unchanging sphere. Every civilization built its calendars, guided its agriculture, and shaped its myths on the assumption that the star overhead was a reliable, static furnace. The first cracks in that belief came from observing tiny imperfections. These dark anomalies drifted across the blinding yellow surface, suggesting the sun was changing. Early astronomers tried to explain them away as passing planets or strange shadows. But in 1843, an astronomer named Heinrich Schwabe tracked them long enough to notice a rigid, repeating sequence. The spots would multiply, fade, and return. The math revealed a strict timeline. Roughly every 11 years, the star transitions from a quiet, blank slate into a highly turbulent, scarred landscape, before eventually calming down again. This predictable cycle dismantled the idea of a solid, quiet star, proving a dynamic machine with a regular heartbeat exists beneath the burning surface. To understand that rhythm, we have to look deep inside the star. The sun is composed of plasma, a highly charged fluid gas. Intense heat from nuclear fusion in the core continuously pushes this plasma outward in violently boiling convection cells. Because plasma carries an electric charge, its constant physical movement generates intense magnetic fields. This churning turns the entire star into an enormous fluid magnet. Due to its fluid nature, equatorial plasma rotates faster than the poles. This mechanism grabs vertical magnetic lines, stretching them horizontally around the star. Eventually, immense tension forces these tightly wound bands to bow outward and violently puncture the surface. The dark sunspots we see from Earth are the visible entry and exit wounds of these broken magnetic loops, the exhaust of a deeply twisted internal engine briefly breaking down. This layout shows the induction equation for magnetohydrodynamics, mapping out the physics of this chaos. It highlights a constant tug-of-war. Plasma velocity twists the magnetic fields, while magnetic diffusion tries to smooth them out over time. For centuries, astronomers believed this 11-year process of tension and release was a simple, infinite oscillation that repeated without change. However, that 11-year pattern is actually only half of a larger 22-year event. As tangled horizontal fields near the equator reach absolute peak intensity, the original vertical field lines anchoring the north and south poles weaken and collapse entirely. At the climax of this internal breakdown, the star's entire magnetic structure reorganizes itself. The internal north and south poles swap positions. Every 22 years, the sun executes a complete systemic reboot of its entire magnetic identity. When those tangled field lines snap and reconnect, they trigger coronal mass ejections. These eruptions launch a massive, dense cloud of highly charged particles into space, carrying energy equivalent to billions of nuclear detonations. Earth orbits directly inside the extended atmosphere of the sun, placing our planet squarely within the active blast radius of its solar cycles. In 1859, a massive solar storm collided directly with Earth in an incident known as the Carrington Event. The raw voltage from the storm slammed into the planet's magnetic field, inducing wild electric currents through the ground. Telegraph networks failed across the globe. Operators were thrown back by electric shocks, and surges caused paper records to burst into flames. A solar storm successfully crippled human communication infrastructure decades before civilization even connected to a broad electrical grid. If a storm of that exact magnitude struck today, the resulting geomagnetic currents would cascade through our low-orbit satellites, disabling global GPS navigation and instantly grounding international aviation networks. On the ground, a direct strike could melt the copper internals of heavy electrical transformers. These components are difficult to replace quickly, making a permanent grid overload a realistic threat. Predicting the next strike remains extraordinarily difficult. Because plasma turbulence operates across star-sized scales, the mathematics becomes strictly nonlinear. A tiny instability can rapidly evolve into a massive eruption, making exact forecasting impossible. Observations of distant stars reveal even more volatile behavior, with superflares thousands of times more powerful than anything in our recorded history. Humanity has observed the sun for only a tiny fraction of its total life. We may simply be living through a miraculously quiet window in an otherwise violent existence. Modern civilization exists at the mercy of a violent, twisting magnetic engine, whose reversing heartbeat dictates the safety of our entire technological era.